Very excited to do this. I've been living in this world of fine-grained complexity for the last 12 years, and I like it. I hope you will like it too, and I'm excited to have 50, 60 more experts by the end of the week to work on this topic with us. So I want to introduce the team. So Nick, come. So you will see Nick, I guess. He will be teaching about half of the lectures. And the TAs, if you can stand up just so they see you. So, if you have any questions, feel free to ask during the talks, but then also after to any of us and the TAs. And there will be like problem-solving sessions, and the TAs will be helping you with everything. So. Okay, so this is like the first lecture of this tutorial. So we did some welcome. And then the next part will be the main part. I'm going to give you an overview of the field before we dive into like specific results and topics, just to give you a broad picture of what's happening. Okay, so before going into fine-grained complexity, let's look at traditional complexity theory, and most prominently the theory of NP hardness, which we love it, right? You can't graduate with a bachelor in CS without learning about it. It's super, used all the time. And this theory tells us that there are problems, there are easy problems and hard problems. So there are problems here that are on the right, for which we have polynomial time algorithms. So for each one of these problems, you can design an algorithm that solves the problem in the worst case correctly on every input, and in the worst case, on every input, the running time is polynomial. And then on the left, we have problems that for which we cannot do this. It's not known how to do it. And these are hard problems like SAT, subset sum, and so on. And this theory tells us that these problems are probably cannot be solved in polynomial time. So and like the formal evidence for this is in the form of like if we could solve them, then something very surprising would happen. P equals NP. There's a big class of NP complete problems, which all of these belong to. And then all of those problems would suddenly be solvable fast, also in polynomial time. And these problems are very famous. People have worked on them for decades, and no one knows how to solve them in polynomial time. And so this is considered a very surprising and unlikely consequence. Okay. And yeah, so we love this theory. It's not just in theory. If you write papers in databases or machine learning or whatever, you have to know about this. You can't be like, here's my problem. I'm going to solve it with this heuristic or with this approximation. If you don't also say, oh, by the way, it's an NP-hard problem. That's why I'm using a heuristic. A heuristic is something that it works usually, but you can't prove that it always works. Or an approximation, it's like you want to compute something, you can compute something that's roughly correct. And these things you do, and these are great, of course. But the first question is, okay, can I do it like in the worst case, optimally, correctly, in polynomial time? If you cannot, if it's NP-hard, okay, then you do all these other things and so on. These are great. Okay, but now let's look at the class P. So what's going on there? Okay. So for each problem here, we have some running time, and we could try to ask, can we do better? And so the idea is like in the 70s when this classical complexity theory was around, the thinking was that once you have polynomial time algorithm, that's it. That's efficient. Because I guess the data was kind of small, so any polynomial, if it's n squared, n cubed, or n to the 10, that's kind of fine. Whereas now in this more modern fine-grained complexity, we are not satisfied. For us, efficient is linear time. You read the input once, maybe a constant number of times, and you get the answer. And so we try to classify the problems based on the exponent. So whether it's n to the 1.5, n squared, and so on. We would like to find the best polynomial with which we can solve problems. And you can say like, okay, the past, the data was small, so like any polynomial was fine. Now we have big data, so even like n squared could be inefficient. And so here's just one example of one of my favorite problems in P. So in this talk, I will mention a bunch of problems, like don't worry about the definitions and so on. In the later talks, like we will focus on problems, and you will have to kind of think about them deeply. But so here's just a problem. It's longest common subsequence. You have two strings of length n, and you want to find the longest string that appears in both of them as a subsequence. So, for example, this is a subsequence that appears in both. It's like, you know, you're trying to find the matching between the two strings. You want to find the longest such sequence. So it's a problem you can solve in polynomial time. And I guess like in any algorithms course, you probably have seen these kinds of things. You do some dynamic programming. So here, just to remind you what dynamic programming looks like, you know, you define some matrix, and you know, the ij entry is like the optimal solution for the suffix, for the prefix from 1 to I, and the 1 to j in the other string, and then you know, you can compute these entries like by looking at a constant number of previous things. And so this table has size n squared, so that's why it's n squared. Okay, so great, it's a polynomial. Can we do better? It's a very simple problem. Probably the simplest problem on strings that we currently don't know how to solve in linear time. So, and in the 80s, there was a paper shaving some log factor. So instead of n squared, you can somehow save in the computation, like fill the matrix like with blocks, like log n by log n blocks, and so on, and you shave some log factors. In this week, we will not be excited by log factors. So we'll mostly ignore them. So for us, okay, it's n squared. Like, we will care about the exponent. The exponent is 2. So can we do better? Can we do linear time? That would be the best. And so why should we care, right? It's n or n squared. And so if you came here all the way, you know, I guess you care. But just in case you want to tell your friends, so here's one reason or one example where it kind of matters. And there's many. It's just like an anecdote, really. But so it's a problem from bioinformatics. It's like a generalization of the previous problem. It's just a bit more complicated. So again, you have two strings. They are DNA sequences now. And you want to find the substrings that are most similar. And similarity is defined with some kind of scoring matrix. Like if you match A and C, you get some score, G and T, whatever. And again, you can solve it with dynamic programming. But the point is, the DNA sequences are very, very long, like millions or billions. And then n squared is not, you can't just run it like it takes hours or more. So if you search the name of this problem, local alignment, in Google Scholar, you get this paper. It's a paper like with this one paper with one algorithm called BLAST. It has the largest number of citations I've ever seen for an algorithms paper. So it's just an algorithm that solves this one problem, and it runs in linear time, not in quadratic time, but it's a heuristic. So like it's a well-defined problem with this scoring function. The answer you get from this algorithm is not going to be probably not going to be the optimal, but it's like good enough. People use it all the time. It's because it's fast, because you know, DNA is so long, they have to run linear time, not quadratic. So it's just an example where it matters. And you know, when you look at this kind of situation, as a theoretician, like it's really begging the question, why can't we solve this one problem in linear time and optimally with a correct algorithm, not a heuristic? And that's kind of the kind of questions that fine-grained complexity is trying to answer. To say, in this case, to say, well, it's not possible because something very surprising would happen. So, you know, that was just one problem in the class P. There's many problems. They're all great. They're all fundamental. You know, many of them have, the algorithms for them haven't improved in many decades. So these are very difficult problems to solve faster. But we also, you know, it would be good to solve them faster. And so for each one, we could ask the same thing. And like before fine-grained complexity, like the class P was this kind of mess. It's just like a sea of problems. So what are the connections? Like which ones we expect to be solvable fast? Like, let's say you wake up, you're an algorithms researcher, you wake up in the morning. Which one of these should you work on? You know, you could pick any, like whatever. Like you spend some months working on it, years. You fail like all the decades before you have failed. You wake up the next morning, you pick another one, and it's like there's no theory guiding you which ones are more likely to be solvable, which ones are harder than the others, and so on. Okay, so we want like a complexity theory for P. So we want to be able to take a polynomial time problem. Let's say it has some running time, let's say n squared. And we want to be able to give formal evidence that we cannot solve it faster. You want to prove a theorem that means that you probably cannot solve this problem in subquadratic time, n to the 2 minus epsilon. So again, I'm ignoring like log factors and sub-polynomial improvements. Yeah, like I would be excited if it's 1.99. Like I would want a theorem that says you cannot do it in 1.999 for any 9. If I have such a thing, this would be like a tight kind of lower bound for the algorithm. Okay, but so how do we do this? So how do we get n squared, n cubed lower bounds? And like the best thing would be to just prove it, like prove it with math, like prove unconditional lower bounds. Like any Turing machine has to run this many steps to get the answer, or any circuit, Boolean circuit has to have this size to compute this function. That's great, and that's what complexity theorists have been trying to do since the beginning of computer science. And we know some things along these lines. So we know this time hierarchy theorem that says that if I give you more computation time, you can compute more problems. So there are problems you can solve in n squared time, and you cannot solve in n to the 1.9. And there are problems you can solve in n cubed, and you cannot solve in subcubic time for any kind of bound. The problem is these are always artificial problems. You prove them with diagonalization. So it's like we don't know these kinds of things for any natural problem, any of the problems we do care about. And in fact, even for SAT, the famous NP-hard problem, for which the best running time is exponential, we cannot prove an n squared lower bound or an n cubed lower bound. The best lower bound for SAT is 3.1 times n. It's like a linear lower bound. So the state of the art is really, really far from giving us satisfactory answers. And these are very difficult questions. People are working on them, and people will continue to work on them, and hopefully we will get these kinds of results, which would be great. But if you want a theory like that gives you answers now, today, or in the next years, then we have to do something else, it seems. So another suggestion that maybe you're thinking of is you've seen this n log n lower bound for sorting, comparison-based sorting. So if you want to sort numbers and you're only allowed to compare numbers in the array, then you're going to need n log n comparisons. So these are like lower bounds for specific type of algorithms. You say what the algorithm can do, and then you prove that the number of steps has to be this much. And these things exist. There's many such results. The problem is they are not general. So you're restricting the algorithm, and specifically for sorting, there are algorithms that deviate. So they do some hashing or they do something, and then they break these lower bounds. So it's not general answers. And moreover, for problems like the bioinformatics problems, it's not even clear what the operations, like what's the restriction on the algorithm that we should talk about. So this is not what we're going to do. And instead, what we will do is look at NP completeness, NP hardness, and try to imitate it. So there we also don't have unconditional lower bounds. What we have is reductions. We have conditional lower bounds, right? So how does it work there when you prove that something is NP hard? So you start with some conjecture, some assumption. P different from NP. SAT cannot be solved in polynomial time. And then you show a reduction. You take SAT and you reduce it to your problem, and then the conclusion is that, well, if my problem was in polynomial time, then SAT is in polynomial time, and that refutes that implies P equals NP, refutes the conjecture. So this reduction is the evidence that your problem is hard. So reduction from SAT, a famous problem, to your problem. And so here we're going to do the same thing, but in a fine-grained way. So we're going to do fine-grained reductions. In the sense that, like here, the reduction could have been at the polynomial blow-ups, polynomial time, and now we will be very careful about the blow-up in the reduction. And then we would be able to look at, or we will have to look at more fine-grained assumptions. So the conjectures that we will do are not just like, SAT is not in polynomial time. We will say something like more precise, like SAT cannot even be solved in 1.99 to the n time. So 2 to the n is trivial, so you cannot do even a little bit better. Such a thing, such a running time would not imply p equals np. It would not imply anything about np completeness. But so we make such strong assumptions, and then with fine-grained reductions, we can get the results we want. So we could say that if my problem is in linear time, then because of some reduction, fine-grained reduction, then this very strong assumption about SAT would be false. So you'd solve SAT a bit faster. And so here's one example, which we'll talk about later in the week, but just to give you a flavor of what's the kinds of results. So for this bioinformatics problem, there's a theorem that says if you solve it in subquadratic time with an exact, correct algorithm, then you solve SAT faster. Then you solve SAT in 1.99 to the n time, which is fast enough to refute this assumption, this stronger version of p different from n. So SETH is this strong exponential time hypothesis. Right, so there's like 3 levels of conjectures. The p different from np said SAT is not in polynomial time. Then there's ETH, the exponential time hypothesis, which says that you need exponential time for SAT. So you cannot do 2 to the root n, which would be sub-exponential. And then strong ETH makes it even stronger. It says the base of the exponent is 2. It's not like less than 2. So just in a little bit more detail about this conjecture. So we will talk about this in Wednesday and Thursday. They will be devoted to this conjecture and all its consequences. Just to give you a flavor, so it's a conjecture about SAT, K-SAT. So you have this CNF formula, but it's K, not 3. Maybe you reach to 3 SAT, where each clause in the formula has 3 variables. Here it has K variables. And the reason we look at K is that, well, for 3 SAT, there are faster algorithms, which we will tell you about on Wednesday. So for 3 SAT, you can do a bit better than brute force. Then 2 to the n is brute force because there's n variables. So you try all possible assignments to all the variables, and you check if they satisfy the formula. So you can do things more cleverly, but the running time goes up to 2 to the n when k increases. So the running time has this form, which goes to 2 to the n as k grows. So then these people, these complexity theorists, 20 years ago, they suggested this hypothesis. They said, well, maybe it's inevitable. There's no epsilon greater than 0, such that as k grows, the running time is 2 minus epsilon to the n. So it has to be of that form. And just kind of like a historical comment here, like this is a conjecture that started from complexity theorists. They were not thinking about fine-grained complexity. Like when they put it, they were just studying SAT. It's a problem that complexity theorists study all the time. And they were like, okay, we don't know how to do it better. Maybe this conjecture is very strong conjecture is true, and let's study it about SAT. And it took 10 years or so until people started using it to get conditional lower bounds, like we will see in this week. But it kind of makes sense, right? SAT is like super famous. People have been trying to solve it. There are even these competitions. Every year there's a competition of SAT solving. People come up with new ideas to solve SAT, and none of these ideas can break it. So it's kind of a well-motivated conjecture. Okay, so before, right, we had this mess, we had all these problems, and now we can draw nicer pictures. So with the results you will see in this week, we can draw these pictures, where we have some conjecture on top. Like in this case, it's about SAT. And then we have an arrow to a subclass of P. And the meaning of this arrow in this class is that if you solve any of these problems faster, you improve the running time we know today. Some of these are n squared, some of these are n cubed. If you improve that, you break the conjecture on top. Or in other words, you wake up in the morning, don't pick one of these problems unless you are brave enough to attack SAT. Before solving any of these, you first have to solve SAT. It's only going to be easier. And I'm not going to go over this list. We will see many of them, but the point I want to make is that these are very diverse problems, like touching pretty much every area of computer science by now. So some pattern matching, graph algorithms, bioinformatics, geometry, some machine learning and stuff. So ideally, hopefully, thanks to this workshop also, it's going to spread more, and then In every community, people will not write papers and come up with n squared or n cubed algorithms without also saying, like, look, okay, they solve it only in n squared or n cubed because there's this lower bound that says you cannot do better. So that would be great. Unfortunately, we are not going to be satisfied with one conjecture. Like, this will not be enough to prove all the results we want. And in this field, there's like 3 main conjectures that people have used, which we will talk about in this week. So beyond the Seth, there's 3-sum and APSP. So I'll briefly tell you about them. So again, these are like conjectures about specific problems, famous ones, like core problems. And for a large class of other problems, you shouldn't work on them until you break that conjecture. So 3-sum is like a problem about numbers, and APSP is all pair shortest paths, a problem about graphs. So let's start with 3-sum, which will be the focus of today. So after this intro, we'll be talking about 3-sum. So here's the problem. You're given a set of n numbers. You can think of them as being integers, doesn't matter. And the question is, are there 3 that sum to 0? So in this input, like the green numbers, they sum to 0, so it's a yes instance. So you get this set, and you have to say yes or no. Does it have a 3-sum or not? And yeah, so we'll talk about later. There's an n squared solution. Like, the trivial is n cubed, but there's n squared. And the conjecture is that you cannot do n to the 1.99. And historically, this is a conjecture that actually kind of started fine-grained complexity in some sense. So people have looked at it in the 90s, but only in a specific community, in computational geometry. And this is not a famous problem. Like, it's not SAT, right? It's just like, it looks like a toy problem, really. Right? So what happened there is, like, people in computational geometry, they were working on all these problems, like lines and the plane and the triangles and stuff. And they would solve some case, but then it wouldn't generalize to the next case. You can solve like lines, it doesn't generalize to hyperplanes or triangles or whatever. And then there was one workshop in which the community gathered, and then people were telling each other, look, like, the reason I'm not able to solve this thing is because of this hard core, which is like, then they isolate it as the 3-sum problem. And then they wrote this paper with like 20 different problems that are all hard because of 3-sum. So it's like, it was like the one thing that the community was stuck on. It's like the simplest thing that they couldn't crack. And that became like a famous conjecture. And since this is 30 years ago, and since then no one has been able to crack this problem. So that's 3-sum. And then the third one is all pair shortest paths. So this is kind of different here. Like, it's a famous problem. If you have a graph and you want to compute distances, like APSP is like the problem you want to solve first. And this is the problem you have seen in your algorithms courses. Floyd-Warshall, Bellman-Ford, these kinds of algorithms, they are solving this problem. So you get a graph. It has n nodes, n squared edges with weights and stuff. You want to know for every pair what is the distance. So you can do it in n cubed. One easy way is, like, for every node you run Dijkstra. If we don't care about logs, so you get n cubed log n. So it's kind of easy. And the people have been trying to improve this n cubed. There's a very long sequence of log shaving results. This most recent one shaves 2 to the square root log n. This is more than polylog for any log, but it's still not a polynomial shaving. And the conjecture is that you cannot do better. So we will talk about this conjecture tomorrow, actually. And it has many consequences. OK, so that's kind of like the end of this intro. So we had the mess, and now we have much more structure and understanding and so on. Okay. So next I'm going to give you some kind of remarks about the tutorial and stuff like that. Do you have any questions about what I said so far? It was at very high level, so it's fine if, it will all be like, many more details will be given throughout the week.
Is there, like, among these 3 conjectures, is there do people kind of have this sort of like an ordering of which they believe more?
Well, I think it depends on the person. Some people have different orderings. It's nothing, and that's one of the other things. So, I mean, in the tutorial, like we will kind of try to give you like the details. This is like the basic, you know, theory. But then there's many other things you can ask, like what, you know, why 3, why not 4, why not 2? Like, can we connect the conjectures? Can we find problems that are like in the intersection, like that are hard under multiple conjectures? There's a lot of theory that one could ask about the theory, and we'll discuss it. So, and actually, like the structure of the course is like the mornings we will have some technical talks that will be like whiteboard talks that will kind of dive into these conjectures and the basic stuff. And then in the afternoons, we will have like a slides talk, which will be more high level and give like a broader picture of things. And then we will discuss these like advanced questions.
Classical complexity theory we have the book of Gary Johnson that used the resource of many other research. I want to know, is there a source, something like it, a book that has a lot of problems with showing their fine-grained complexity as the main resource of fine-grained complexity, or not such?
No, not yet. This course is going to be some resource, hopefully, but it's not going to be extensive, you know, like what you're asking. But yeah, hopefully it will happen.
So I have a question. Is there any particular reason why they said it's true, or it's just like a couple, like a group of people try to do it for a long time and cannot solve it and make it too late? Or is there any other reason that you?
Yeah, that's a good question. Like you could ask it about any of these conjectures. Like what kind of evidence do we have for them? I think the strongest evidence is what you said. Yes, like communities have thought about them for decades and they couldn't. And what that means is really like every algorithmic technique we have, and people are designing new algorithmic techniques all the time. All of these techniques, they fail to break these conjectures. So that's kind of a different way to say the same thing. In terms of other evidence, like if you refute it, what happens? There is some consequences. Like if you refute Seth, some things will happen. But these they're like somewhat, like, you know, the world will not change. I mean, you would get some kind of breakthroughs in complexity theory for circuit lower bound, unconditional lower bounds. But these are not, you wouldn't get P different from NP, for example. Like, you wouldn't get like, but it would imply some interesting things. Yeah. Okay. So, yeah, I mean, we're here all the week, so, you know, whatever like kind of questions, high level you have, just ask us. So some technical remarks about the tutorial. So as I said, we will ignore log factors like polylogs, even 2 to the square root log. Anything that's n to the lit log 1, we will not care. And this is about the tutorial, but also about the field, the fine-grained complex. That's kind of the way we look at things. And what that means is, like, when you do a reduction, it's okay if you have log factors in the reduction, because the reduction is trying to say if you solve this in faster by n to the epsilon, then you solve that faster by n to the epsilon. So if you have a polylog factor in the reduction, that's fine. And this is for 2 reasons. I mean, first is like, you know, let's just try to get the polynomial right, and then we can worry about the log factors. That's the first reason. And the second reason is, well, we need log factors for the reductions. So you will see some reductions today, like Nick is going to show you some cool reductions today where you really need like log factors. It seems hard to not lose them. So, and you know, it's not, shouldn't be somehow taken for granted that we can build such a web of reductions when the reduction has to be so strict, so fine-grained. Like with the NP completeness, everything was equivalent, you know, but then we had polynomial blow-ups, so our life was easy. And so if we somehow don't allow log factors, then it seems like it'll be much harder. So that's kind of the reason. Another thing, so these comments, like, maybe they will not mean much to you today, but throughout the week, like, I will say, I told you this and that, so that's the reason I'm telling them now, but just, so don't worry if you don't care about this. So the other thing is randomness. Like, we will allow randomness. Like, we will not care if things are randomized or deterministic. So if we say something can be solved faster, it's fine if it's randomized. That's interesting enough. And like, if you have a reduction, if it's randomized, that's fine. We don't care. And okay, and then what are the reasons? Again, a couple of reasons. First is like these conjectures. People don't know how to break them even with randomness. So even with the randomized algorithm, so randomized algorithm is more powerful than a deterministic algorithm. Even with randomized algorithms, we don't know how to break them. So if you have a randomized reduction to some problem, and then the consequences, if you solve it faster, you get a randomized algorithm for the conjecture, that's fine. That's interesting. That's interesting. Another reason is, in general, in complexity theory, the common belief is that randomness doesn't help that much. So there's the class P, the class BPP. BPP is what you can solve in polynomial time with randomized algorithms. We believe that P equals BPP. So randomized algorithms may be like much easier to design, or maybe today we have gaps, we have problems we can solve randomly, but not deterministically. But like at the end of the day, like it's not going to matter. It's not clear that when you are fine-grained, this is true. Like, it may be that you have to lose an n factor to de-randomize and stuff. So, but we will not worry about this. We will use randomness like very freely. Most of the time, we can de-randomize it with more work, with some technical work, which we will not get into mostly. And then finally, like about the model, we're not Turing machine. We're working with the word RAM. If you don't know what it is, that's even better. It means like you know what it is. It's like what algorithms designers think about. It's like you have random access. You can have these log n size words that store numbers, whatever. You can access whatever you want and add numbers in constant time and whatever. Like this is these things. The people worry about the word model if they want to care about log factors, or if you want to do hashing and you don't want to allow randomness, then have some logs or whatever, we will not care. So it's the standard model. And when you talk about numbers, we will assume that numbers are integers and some polynomial range, like n to the minus n to the 10 to n to the 10. And then you can store them with like 10 log n bits. So it's like just the standard stuff. Okay, and now another thing that like maybe you don't care about now, but maybe later you will want to think about. So like, what is a fine-grained reduction? And the point of this slide is to show you that like, there is a definition. Like, you can formalize what it means. Throughout the week, we will not care about this definition. Like, we will just do reductions, and it will be clear that we're doing reductions. But like, here's the definition, just for you to, if you are someone who really wants definitions and formality and stuff, here's how you can formalize it. So so we want a reduction from A to B, and it should be fine-grained, and it has this A and B subscripts. So A is a problem with running time n to the A, like maybe n cubed, and B is maybe n squared. It could be that they're both n squared or n cubed, or it could be different. The meaning of such a reduction is that if you solve B faster, like better than its running time n to the B, then you solve A faster, better than n to the A. So we want this definition to give us this theorem that if we have a reduction from A to B, and we solve B faster by some n to the epsilon, then we also solve A faster. So that's like the main thing we want from a reduction. And so pictorially, like this is what's going to happen. You have your input to the problem A. You are going to make calls to the problem B. So you run some computation. You get some instances, these yi's. These are instances of B. You ask an oracle to B, and you get answers. And it should be a fine-grained reduction. So the running time of such a thing should be faster than n to the A, of course, because otherwise, like, it's not proving what you want. But also the sizes of these instances, they should be small. And formally, you want them to satisfy this thing. So if you take each one of these instances, you solve it in n to the B minus epsilon, where B is the running time of B. So you solve it a bit faster than what you know how to do. Then the total would be less than n to the A. So that's like formally what, if this is satisfied, then you have the right reduction. And then you also want a theorem that says, like, if you can reduce A to B, and you reduce B to C, then you can reduce A to C. Right? That wouldn't make sense if that didn't happen. And so there is such a definition. So here's the definition, suggested by Virginia Vasilevska and Ryan Williams. So it's basically what I was saying here. Fine-grained reduction from A to B is like an algorithm for A that makes Oracle calls to B, and then for every epsilon there's a delta such that this is satisfied for the epsilon delta, and this is an algorithm that's correct, and it's fast. And just one thing to comment here is that we'll do randomized reductions most of the time. So then what we want is that the algorithm is correct with high probability. The probability that it's not correct should be less than 1 over n to the 10, some small polynomial. Okay, so that's the end of these remarks. Just going to end with explaining the objectives we're trying to get from this course. So yeah, as Karthik was saying, ideally we want you to be able to prove your own fine-grained reductions when you go home. And I guess the first goal is for you to understand what fine-grained reductions, what are known and so on. And so towards that, we will try to highlight the simplest hard problems. So what it means is these problems in blue. So if you look at SAT, so there's this intermediate problem called the OV, orthogonal vector. So we'll talk about it. It's a very simple problem that then you can reduce it to a lot of problems. So it's that is the problem you should focus on. You have your problem, you want to show a hardness, you should start with the easiest problems to reduce to. So we'll highlight these problems, OV, negative triangle. So yeah, that's the plan in terms of the days. So today we'll talk about threesome, tomorrow APSP, and then strong ETH is the most famous and has the largest number of applications. So we'll spend 2 days talking about it. And so the second goal is also to give you, an understanding of what's happening in the theory beyond the basics, what researchers are thinking about these days, so that you can, read papers and so on. And this is really the purpose of the afternoon talks, the more high-level talks, and also on Friday we will talk about this. And the most important goal in my opinion, is spend this week we're gonna really be having fun with the most basic problems. Like threesome, it's such a beautiful problem. It's so easy, it's so simple. And we'll really be spending the whole time thinking about such problems. So hopefully it will be fun. So that's it. Let's take a break, and then we'll go on, switch gears, and we'll talk on the whiteboard. So 10 minutes. So let's be back at 10.